within minutes, there'll be a significant drop in the contaminant levels in this area.
I will be breathing in nanoparticles as I stand here. When I go back in the car, our roads are full of nanoparticles from exhaust. What is new is the deliberate engineering of these very, very small particles to have enhanced or even novel properties, and the uncertainties that that introduces in terms of the potential risks to the environment and health.
There's two aspects to these solar technologies that are incredibly exciting. The first is just raw performance to cost. The other thing about having a flexible solar cell or a paintable solar cell is that it just allows your imagination to go wild. Imagine if you could wear clothes that were solar energy harvesters and that would charge up the batteries of the mobile devices that you were carrying around. Imagine if you could create a sailboat whose sail was also a solar energy harvester and can charge up the battery on your sailboat. The imaginative possibilities that emerge when you start to make low-cost, flexible, and high-efficiency solar cells simultaneously are really limitless.
work in an environment where it crosses the disciplines. Solar to us is very important. Basically, we had the challenge from the chairman of CAUS board telling us that he wants Saudi Arabia in the future to export the same BTUs that we are exporting from fossil fuel in the form of solar energy. So I don't know how big that challenge is, but it's really a tall order challenge.
It's a bit like when, I guess it would have been in the 1950s, people wondered whether one could go to the moon. And it became clear that there's no physical impediment. There's no laws of physics that would prevent that from happening. And it became a technology challenge. Energy today is a $9 trillion industry. I can't think of a bigger sector of the economy. I mean, it's absolutely huge. It's something we almost don't notice because it's so much around us and we take it for granted. Does the eel show you like the elemental makeup of glycogen, or sort of structure and composition at the nanoscale? How do you actually make the connection to function? Actually do all the work. The sun's power reaching the Earth is really incredible. There's 10,000 times more solar power reaching the Earth every day than we use across all our energy habits. Another way to put the same idea is that as much sun hits the Earth in an hour as we consume in a year. One of the phenomena at the heart of nanotechnology is that we can shape matter. As a consequence, in my lab, when we make 3 different batches of nanoparticles, we can program them, each to be responsive to different slices of the sun's spectrum. And so it turns out that fully half of the sun's energy lies in the infrared frequencies and the other half in the visible. So my research acknowledges that we need to capture all of that energy if we're going to make an efficient solar cell. So the major differences in making quantum dot-based solar cells relative to existing approaches, the first is that we actually do work with individual nanometer-sized crystals, and they're individually packaged. So each one is in a position such that we can just coat it, spray it, if you like, paint it onto a backing. And then also, by virtue of their lower cost, you won't hesitate to deploy them across the entire surface of the building. In fact, if they're cheap enough, if there's a little bit of power to be had from the sides of the building, you might even put them there too.
I've been living in this city all my life. Now, over the years, I've seen changes I never would have believed. Take power. My grandson just assumes it comes from the sun. But it wasn't always like that. There used to be coal and oil, and who could forget all the trouble with nuclear? After that, energy saving came back. People bought all kinds of do-it-yourself solar stuff, like my mini panel. It's basic, but I'm still using it. Then came the Nanoflex fabric balloons. At the beginning, they were kind of modest. My neighbor Sam was the first person I know to try one. Pushy guy. Always wants to be first with everything. Yeah, did seem like a bright idea. But right away, there were tensions. And in no time at all, there was trouble.
Sam! It's that damn balloon of yours! Keeps blocking the sun from my solar panels. Now there's no hot water.
Hey, sunlight is first come, first served. Go get yourself your own balloon. Hey,
You can't hog our sunlight.
hey, I can't help it if my balloon happens to be bigger than your panel.
I'm gonna tear your damn balloon to pieces. Oh, shut up, you solar thief!
No, don't.
Sam's Nanoflex balloons were just the beginning. People started to think big. And do I mean big? Why stop at balloons and solar panels when you can have your very own nano-solar reflector airship? Solar guzzlers. That's what they are. Swallowing up the sky.
We're in danger. We're in danger because we need water, and the only source we have is poisoned with arsenic. This is the city where I was born, and right now my responsibility is to make sure that everyone at their homes have water every time they need it. We are having water from 700 meters deep wells, and the concentrations of arsenic at that levels are very, very high.
The water coming out from this water treatment plant, it's pretty clean, but we still have a problem with the arsenic. And we cannot face it with the available technology because it's too expensive for us.
bet one of the rice professors can tell you better.
That's a good question. We can see those materials using our very latest instruments, so we can actually know a lot about how small they are because we can go down to those length scales. But more than that, they're strange. Materials on the nanoscale, they interact with things around them very differently, and they don't behave at all like things that are just a little bit bigger. So that strangeness is really the value of nanomaterials. And when you find an application like we have here in Mexico, where that very strange chemistry can be coupled with a really important social need, that's when you have this opportunity to actually change people's lives. Well, I think everybody knows what rust is. We're using a particular form of rust, and nano-rust is a good way to think about it, but it's special. It's special because it's really, really small. And so really what we're hoping to do is by using these nanomaterials that have just in a single small amount, tons and tons and tons and tons of surface area for the arsenic to stick to. It's kind of like an amazing sponge for arsenic.
It's good. Yeah. Well, want to do it right. Yeah.
Water everywhere is getting scarcer. It's getting harder to clean it. You're having to dig deeper to find aquifers that are not already been used by people. And in fact, arsenic becomes more of a problem, like in this community, is they have to turn to deeper and deeper wells. Those always have more and more arsenic. So it's an existing problem, and it's certainly one that we anticipate growing, not just here, but in many, many other regions throughout the world.
Hey guys. Hey Vicky.
How's it going?
It's going. Bueno.
Looks like a column. Muy bueno.
We're hoping to put 10,000 liters through that 1 pound of magnetite. Give me a good twist. Yeah, all right.
You guys ready to clean some water?
Yeah.
All right, it's time to take it to the field.
Took it up.
All right, let's see what happens.
That's pretty good. We're pumping the groundwater directly into the top of our column with the arsenic in it.
Nanotechnology is this capability, this entirely new toolkit that people have available to them. And I think it's going to move into just about every arena, limited perhaps only by the creativity of people and how they take these new ideas and new tools and solve some of the world's most hardest problems.
Taller. Well, on the other side of the building here, they would have had a maintenance yard where they would have cleaned up tools and trucks with a trichloroethylene, which is a chlorinated solvent that's commonly used for degreasing. It's commonly used in dry cleaners. Historically, let's say 20, 30 years ago, when you were done with oils and these kind of liquids, you just pour them on the ground or pour them down a drain, and they let it get into the subsurface. We didn't really understand that these contaminants would persist for long periods of time, that they're extremely toxic.
It's been injecting in for about 3.5 hours. Yeah, as long as the water is moving, it's not going to freeze. So
we're watching for this to turn orange, then it's going to be ready to dissolve. What do you want it at?
turn up the red one. Yeah, it's frozen.
What do you mean it's frozen? These conditions do present significant challenges with the freezing lines, the generator, the air compressor is harder to start. Having said that, though, the contamination is moving over this way here. So the longer you wait, if you wait 6 months, it's going to be that much further down, contaminate more area. So we want to get at it as soon as possible.
So until we get it into the vessel, which is in an exclusion zone, we have to be very careful. That's why we have to kind of stay back.
So this is the exciting time. We're going to inject the borohydride into the synthesis vessel. It's going to turn black. And if it doesn't turn black, you're going to have some worried people here. It's not yellowish anymore or orangey, it's turning black to nanoparticles now. 400, 420 mils in how many seconds? 8 seconds. That's crazy, eh? So we're injecting the nanometals right in here. And what I'm doing is I'm keeping a close eye on the water level because we want to make sure it doesn't come up and spill over the wellhead here. It's going to go in there and it's going to go towards this well here. Just stay there in case it comes up. It'll be like a gusher. So we're hoping that we're going to have a smear zone around this entire zone to attack the contamination in this area. The nanometals that we're injecting today, we inject them in for two purposes. One, to attack the initial contamination in this zone, but then there's going to be some residual nanometals in this area. So as the water continues to flow through here that's contaminated, it'll flow through this residual nanoparticles and they'll be degraded. So further on downstream, the water will be cleaned and you can probably drink it. If you drive around, let's say, and you're at a four-way stop and you see a couple of intersections that are empty with a couple of wells sticking out, that's likely an old gas station that's contaminated where no one wants to go back in there and buy up and redevelop the land because it is contaminated at significant cost. Well, these nanoparticles are very reactive. So once we inject them into the ground, they don't last very long. They'll react with the contaminants in the ground. They'll react with the water, with air, and then they'll essentially become rust. And they'll aggregate together, stick together, and then they'll settle out a solution and dissolve away. So there'll be no problem.
The Nobel Prize was awarded for the development of DDT with the possibility of eradicating malaria. The use of asbestos as a fire retardant had tremendous benefits, but of course with significant impacts on human health. What we're trying to do with nanotechnology is avoid those sort of disappointments, to avoid those sort of environmental impacts. So what we're doing here is testing nanomaterials in a very complex environment. As we use these products, these things will go down the drain, end up in a wastewater treatment plant. The wastewater treatment plant will separate them into the clarified water and the sludge or the solids that come out of that process. One of the things that we're interested in looking at here is what happens when we do apply them to land. How long will they stay there? Where will they go? What kinds of organisms will they impact along the way? When you talk about a nanoparticle, it's all surface. When you get down to a particle that's something like 5 nanometers in diameter, about half of the atoms are on the surface. Nature will modify these surfaces just as much as people will modify the surface. So we can engineer the surface to death, but when we put it out in nature, nature will begin to modify that surface, and we believe that those modifications change the very properties of the nanomaterials.
So we're working with killifish larvae, and we're dosing them with one of our silver nanoparticles and trying to understand how different types of water affect the toxicity of those particles. Over the past several years, we've made a lot of progress in understanding how a particle might affect an individual species, fish, invertebrates, etc., but understanding how it may alter the entire ecosystem or microbial nutrient processing, etc. We're just at the cusp of that type of work. We don't normally regulate most materials before they're released in commercial products in the United States. And so generally, we're left with a situation where we're trying to understand whether products that are already out on the market might pose a hazard to either wildlife or humans specifically. So we have to work very fast to try to understand these questions as quickly as we can. The last thing anyone wants is 30 years from now figuring out that there was a problem that we should have discovered earlier in the process. And so it is definitely a race.
You know what? Some things are never quite what they seem. This park, for instance.
I'm gonna go play. See you later.
I live nearby and come here every day when my grandson's around. He'd play here all day if he could. Now, this park was a wasteland when I first bought my little apartment. That was the only reason I could afford the place. Nobody wanted to live on the edge of a dead zone. It was all fenced up and no one could go near it. But I was lucky. It was chosen for the latest nano-remediation soon after I moved in. The whole area was off limits for years. No one knew exactly what they were up to, but in the end, it was amazing. Magical. to see a dark, derelict space come alive again. A run-down wasteland, transformed into a beautiful park. It's a joy to see my grandson play here with his friends and think back on what it used to be like. But lately I'm not so sure. Protective tents went up again, and the inspectors were back, looking for something. I don't know what. Then the anti-nano troublemakers started. Looks like fear-mongering to me, but fear can be catching. I don't know what to think, as I say. These days, nothing's quite what it seems.
The sources of uncertainty in this area are numerous. We don't know what nanomaterials will be made. We don't know how they will be used. We don't know how many will be used. We don't know where they will go. We don't know who they'll impact. There are a great number of unknowns. Some of the unknowns are unknown. Some of the unknowns are known. So what do we know and what do we don't know, and what have we not yet imagined?
We see a lot of patients come into our coronary care unit with acute heart attacks, severe heart attacks, life-threatening heart attacks. And actually, if you look at what they're doing in the hours before they come in to have their heart attack, they're 2 to 3 times more likely to be in traffic. What's she doing when she got a chest pain?
That was a good question, actually. We were basically driving home and caught in traffic, and she suddenly started getting some chest pain.
Yeah. What we now understand is that there's very small particles that are in the diesel exhaust of traffic. These nanoparticles, we call them combustion-derived nanoparticles because it's when the engine burns them. So when people breathe in these combustion-derived nanoparticulates in the air, they can influence the lung, cause inflammation in the lung, and that then causes a cascade of effects that can affect the heart and trigger the heart attack. We also believe that these nanoparticles are so small that they can actually fly across the blood vessel wall, because in the lungs, the blood vessel wall is incredibly thin. So we think these nanoparticles, when they're in the bloodstream, can actually trigger these plaques, this fatty deposit in the artery, to burst open, and that can cause a heart attack to occur.
Morning, Roger.
Hey.
Hi, my name's Dr. Barnes. I'm one of the researchers involved in the study. Just before we take you out on the walk, we need to put an ECG machine onto you and a blood pressure cuff just to measure your blood pressure. You feeling okay?
Yeah, a bit Frankenstein-like with all these.
Sure,
Okay.
You're not the first to say that. And so I think when this bus goes past, it would be interesting to see what count we get up to. We're about 30,000 at the moment. Yeah, and you can see it's jumped up quite a bit there. So it jumped up to about 48,000. Are you feeling okay, monitor?
Yeah, no, it's fine.
Actually, inside a car, the pollution levels are much, much higher than outside the car. They're about 4 or 5 times higher inside a car. So there are 4 or 5 times as nanoparticulates circulating.
That's the famous Radcliffe Observatory over there. Keble College we're going past now. Somerville College where Margaret Thatcher was. One of our favourite pubs. It's a nice tour, isn't it?
It's a great tour. Right to me, actually.
The thinking about nanotechnology for me, and I guess many of my colleagues, is a 24-hour-a-day exercise. We can never get it out of our minds. We're thinking all the time about potential applications of the material we're working with, or if we're seeing problems, we're asking, how can nanotechnology solve those problems? What new property can we endow in a particle which will solve the problem we're seeing? The fuel on this bus has got cerium oxide particles suspended in the diesel fuel, and the idea started because of a chance meeting in a pub between someone who had this vision of using cerium oxide to improve diesel engines and a former student of mine. Clean emission, no soot coming out of the tailpipe, and we see this as a radical way of improving all internal combustion engines and possibly other combustion as well. If you envisage breaking the cerium oxide down from big lumps down into lots of tiny little nanoparticles, you end up with a very high surface area. And it's that surface area which drives the catalysis and makes it so effective as a diesel fuel additive. We're learning more about the environment that exists, but we're also beginning to understand how we can adapt nanotechnology to clean up some of the pretty dreadful contaminants we've introduced there already. I'm one of the optimists. I think that nanotechnology is going to play a much bigger role in improving the environment than damaging it.
We're beginning to understand more about how nanoparticles behave in the environment. But they're very complex, that behavior is complex. Technology and innovation, like nanotechnologies, doesn't happen in a vacuum. It happens because it interacts with us as human beings. And the key thing is that we understand that we recognize that we all have our faults, and that technologies can sometimes go wrong. They needn't go wrong if we develop them responsibly. And that's the sheer challenge for us now with this, probably the most exciting technology of the 21st century. There have been no reported effects in the environment. No real impacts have been observed. And in fact, we haven't really detected many of these manufactured nanoparticles in the environment themselves. So, from my own personal view, it's not that we've shown that they're harmful or that they pose a risk, it's just that we don't know. Some of the most recent calculations have been that just the safety testing for those nanoparticles that are manufactured in the US alone, those ones that are on the market now, could be between 30 and 50 years and up to $1 billion to complete. It's hard to generalize about how long it's going to take for us to figure out whether nanomaterials pose a risk to the environment and health. But it's going to take decades, guaranteed. It'll be decades before we fully understand, just for the ones that are out there now, and be able to make decisions on that basis.
Hey Magda, what's the ORP? 50. Well, it should be coming any time now. It should come right through. We haven't seen it yet, and I haven't seen it come through here, but it'll be there very soon. It's going to turn black, I'd say, in the next 40 minutes. That indicates that we've got good smearing of this zone for the remediation of the site. We're anticipating a widespread acceptance of this technology because we're able to inject the nanoparticles where the contaminants are. A lot of other remediation technologies, you'd have to dig up an entire site, which is very costly. Then you'd have to do something with a contaminated soil. So here, this is an in-situ technique right in the ground. We can inject them where they can degrade. We don't have to disrupt the whole site.
In this test, the arsenic in the water is converted into arsine gas, and that gas reacts with the test strips on the top of these vials. And so these test strips change color depending on the amount of concentration in the water. So it's kind of like a pH test strip on steroids.
How's it going?
Oh, hey, pretty good. I just got done with the reaction period for the arsenic, so I'm just checking out our results.
Oh, great, great. That's the before.
That's the before, yeah.
We do the after. After our nano-magnetite. Oh, great.
Okay,
yeah, it's all gone.
Yeah, great.
Zero.
Yep, this is zero. So right now there is no arsenic coming out of the column. It's being completely removed by the nanomagnetite.
It's called an experiment, but fabulous. It's a really, really good outcome. So now we just have to keep watching it.
Congratulations.
I think that at this moment in time, we are poised, this is our technology developed. This will be our generation's contribution to the world to take it up that next step. And so yes, I think my kids are going to live a better life because of the kinds of nanotechnology that we have, where we can put it in and solve the problems that all of us are facing.
One of the elements of our work is trying to imagine if you had a nanoparticle in front of you, what would it look like if it were dangerous? Would it be blue? Would it be long? What would be the characteristics of a dangerous nanomaterial? We don't even know that yet. I would be surprised if there wouldn't be some unintended consequence that's going to get past our experimental network. We can't anticipate everything, but we can reduce the uncertainty and we can reduce the impact.
Well, the people that lived and worked in this building behind me have long gone, but they lived in a very different society 80 years ago, only 80 years ago than the one that we live in now. And that society has been shaped by successive waves of technology and innovation, nuclear technology, molecular biology, information technology, and now nanotechnology. And my grandchildren will live in a very different world again, shaped again by innovation and technology. And as human beings, that's what makes us, our creativity and our appetite to move on and be innovative. But we also know that we have to be responsible. With an exciting technology like nanotechnology, we don't want to be left with a legacy for our grandchildren to have to pick up. So a lot of the questions that we have about new technologies are not just technical risk questions, they're philosophical questions. What kind of technology do we want? Is it safe? Should people have a say in shaping technology? Do we live better lives? Does it have unintended consequences? Does it create inequalities? We accept these technologies, we buy these goods, we move on. What we should probably do is be a little bit more reflexive. Think a little bit more about those technologies and about the world in which they are deployed and how we live with those technologies in that world.